Okay, so let's look at one more problem here. This is problem 69 from the text. I drew the circuit kind of big, so I'm going to have to scroll away from this in a second. And so what do we got going here? I should label where V out is. So this is plus minus V out. That's what we're looking for. That's what we're asked to find. Alright, so this is going to still be considered an ideal op-amp, and like usual, we want to put these in phasor notation. So if I look at the voltage source, this is easy. It's 20 cosine 5000t volts. And so this would just be 20 at an angle of 0 degrees. Which, remember, 20 at an angle of 0 degrees would just simply be 20. So that's pretty nice. It's pretty easy for us to deal with that. Okay, so then what else do we have here? Well, we need to figure out what the impedance of this capacitor is here. So, remembering that Z sub C is equal to minus J over omega C, this would be minus J over, well, omega is 5,000 times 0.5 microfarads, and that would be equal to, hold on one second, I do that real quickly. Minus J 100. Oh, I should maybe make a comment here. If you have your textbook, it looks like the negative and positive terminals are connected. That is a typo in the textbook. If you tie the negative and positive terminals together in an op-amp, you're basically doing nothing, especially with one of them grounded like that. So, you know, that's not something you would ever do. And so that is actually a typo in the book. But we get negative J 100. I'm sorry, not 100. Let's try that again. 400 ohms. So let's double check that just to be 100% certain. Yes, negative J 400 ohms is the impedance there. So I'll go ahead and write that as minus J 400. Now, I'm going to go ahead and erase this here. So if you need that, pause the video. Because now let's remember some things about op-amps here. Remember, we don't typically want to write an equation there. I mean, that's our output voltage we want. That is V out at this. But we don't want to typically write a node equation. And the reason we don't is we don't know the current coming in and or out of that op-amp. And there's no way for us to easily determine that. But we do know that here is 0 volts, which means at this point right here is 0 volts. And so what I'm going to do is I'm going to say, okay, well, I'm going to have some voltage here, VA, and then I'm going to try and find V out. So I don't know what this voltage is, but we'll be able to write a node equation here. So I'm going to write here, I'm going to do a node equation right here to start with. And I'm going to go ahead and write the zeros in here. So what would we have? We'd have 0 minus VA over 400 plus 0 minus V out over 200. And this is equal to 0. So then multiplying through, of course, by 400 is what makes sense. And so you'd have negative VA plus, sorry, not plus, minus 2 V out is equal to 0. So solving that, you would get V out is equal to negative 1/2 VA. Now that should make sense to us because I'm going to do a little dot thing here and then I'm going to erase it here. I'm going to cut the circuit here. If I look at just what's inside this box here, that's just a non-inverting amplifier. And we know the gain for a non-inverting, I'm sorry, not non-inverting, it's an inverting amplifier. And we know the gain for an inverting amplifier, it's just negative feedback resistor over input resistance. negative 200 over 400, negative 1/2. So V out, and VA is that input voltage. All right, so that shouldn't be too surprising to us, but I wanted to go ahead and write the equation there, so let's erase that. I'm also going to erase this now, so again, if you need that, pause the video here. And I'm just going to write up, so I don't lose it here, I'm going to write up here that V out is negative 1/2 VA. Alright, so as I said, I'm going to just erase this. Yeah, erase all that. Alright, so now what do we need? We need to write a node equation at VA. And of course, you know, I've stopped kind of drawing these currents a lot in class, but we know that basically we're going to sum the currents leaving here. So we just write down a node equation. So I'd have VA minus, now this is just 20 because it's 20 at an angle 0, so it's just minus 20 over 400 plus VA over negative J 400 plus VA minus 0 over 400. And that's equal to 0. Now, clearly we want to multiply through by something, and in this case, like I've been doing in a lot of these videos here, I'm actually not going to multiply through by the j, I'm just going to multiply through by 400. And so we wind up with VA minus 20. Now this 400 would cancel out, and I'd have VA over negative j, but remember you can move the j's from the numerator to the denominators by simply just changing the sign. So this would be plus j times VA plus VA equals 0. And then I'll scroll this up a little bit to give us a little bit more space. And then solving this is pretty straightforward. We would have 2 plus j times VA is equal to 20. And so then what do we get here for VA? Well, let's do that computation here real quickly. And we'd wind up with 8 minus J4. And then we had that V out was equal to negative 1/2 VA. And so V out is equal to negative 4 plus J2 volts. Now, of course, because we were given the information, we should convert this back into the magnitude and angle form. And so if I do that, convert it back into polar, we get that this is V out is, and I'm going to round it to two decimal places, 4.47 at an angle of, and I'll just write this as 153.43 degrees. Now, because we were given the frequency, and of course we want to write the actual answer, so V out at t, my steady state, actually I shouldn't say V out at t because it's not transient. V out, which is just my steady state, is 4.47 cosine of 5,000 t plus 153.43 degrees. So that one was straightforward here. I encourage you to look at problem 9.71. That's a very good exercise. It looks like it's actually relatively difficult to do, but that should be very similar to non-inverting. And I'll go ahead and tell you what the answer to that is, so you can try and do it and see if you get your answer correct here. So there's actually two parts here. It's part A and part B. Part A for 9.71. The answer for part A is that the output voltage is 7.07 at an angle of negative 8.13 degrees. So I'll let you see if you can come up with that. Maybe we'll start class next Tuesday with that problem. If we do, we're going to do it relatively quickly though. And then and actually I'll go ahead and give you a hint on how to do that problem here. And then for part B, we have that the magnitude of the input voltage there has to be less than or equal to 35.36 volts so that we don't saturate. And it's the same idea with saturation before as far as what we want to make sure to do and not saturate. So just to give you an idea here of how to do this problem and approach this problem, I'm just going to draw a box here. I'll give a real rough sketch of here. I'm not going to put in component values, but this is the circuit diagram. So I'm just going to go ahead and put in R1, R2. There's prob values in the problem in the book here, C, and then I'm going to call this RA, RB. Now, what you want to look at here on this, and again, I want you to work on this problem, is if I look at those two things, those are in parallel. So I could have this become some kind of equivalent impedance Z2 on the feedback path. And then I could look at this R1, and I could write this as an equivalent impedance as well, which is Z1. Not really that exciting because that's just the same. But then, remember what do we have here? When we did this last semester, we called that V+, and we can just get that V+ from a voltage division. V+ is going to be equal to RB over RA plus RB times VG. But then why did I look at this as Z2 and Z1? Let me just go ahead and redraw a portion of this op-amp. And so I'm going to have V+ coming in here, which we determine from the first little voltage division. I'm going to have some Z1 Z2 on the feedback, but this should look familiar to us. In fact, it should look familiar from a video that I did on some circuit simulation. This is just a non-inverting amplifier. So we know that the output voltage here is equal to 1 plus Z2 divided by Z1 times V+. And so we don't actually have to write things down. We could have done something similar on the example that we did here. I just went ahead and wrote the node equations down. Now sometimes you don't get the ability to do that. Sometimes you just have to look at the op-amp and you got to write some node equations down and you don't have any other choice. But I wanted to do a couple op-amp questions here. And as I said, I want to see, and I'm going to ask you guys at the beginning of class if you did this problem and if you could get those answers. All right? So we will start class then also on Tuesday next week talking about transformers.